All right, so in this video, we're going to talk about Green's theorem. Green's theorem is going to allow us to relate a line integral around a simple closed plane curve C now to an ordinary double integral over plane region R with boundary C. Now this first part here, a line integral across a simple closed plane curve C, we've already done that before. If you'll remember from an earlier video, when we computed that line integral and it was across a simple closed plane curve C, what we did is we went ahead and separated it and added it up. And we could do that as many times as we needed to, of course. I think in our example, we maybe had two. But what we're saying now with Green's theorem is we don't have to go through this mess anymore. We can go ahead now and compute this as an ordinary double integral over region R with boundary C. And so this is going to be our setup here for Green's theorem. You can see your traditional setup for a line integral here, the p dx plus q dy. That's going to be the f dot dr from before. And then we've got our setup now as a double integral over region R, partial q partial x minus partial p partial y, and then dA for the double integral that we'll need there. So you'll see the setup here is very, very simple. We've got an example here, and our curve is going to be the boundary region between the parabola and the line. And so to get this thing set up, first thing I'll do is set up my double integral, and keeping in mind that this is going to be our p value, this is going to be our q value. So when I now use the formula, partial q partial x, here's our q with respect to x, that would be a 2x. So we've got our 2x minus, so that minus and that minus are the same, and then partial p partial y, so this will give us a 2y. And it really is that simple in terms of getting this part set up. Now in terms of the bounds, this is going to be what we did from the last chapter. So a very, very straightforward process. If I sketch the region now, here's going to be that parabola, and then here's going to be that line. And so this is our boundary curve, whereas if we would have done this, and that comes into the origin there, had we done this previously, we would have had one of them, maybe this guy, plus the other one, which would have been maybe this guy. Now we're able to do it all together. And so to get that set up, maybe we'll go vertically, which would imply then a dy dx. So the parabola would be on the bottom, the line would be on the top, and you've probably done this example enough already to know that they intersect at 0 and 1. If not, just go ahead and set these two things equal, and then you'll find out. So there's our setup using Green's theorem, which is a whole lot easier than what we've done previously. All right, so now we're going to take a look at a couple different equations here. You'll notice the first one that you see is the exact one that I gave you in the previous screen, and it's also said to be able for us to be able to find counterclockwise circulation. The second one is slightly different. It's the p dy minus the q dx, and it's going to have a different form as well in the double integral setup, and it's going to give us outward flux. Excuse me, outward flux. Now, to avoid any confusion and to convince you that these things are in fact doing what they should be, I would encourage you to take a look at example 4 on page 993, and then it carries on to page 994, and it shows you how these two things are related. But for right now, the setup that's going to allow us to compute counterclockwise circulation most easily will be this, and then outward flux will be this. So let's go ahead and take a look at this example right here where we've got our vector field F, we've got our curve, which is going to be the triangle bounded by these three lines. So if we start here and we want to compute counterclockwise circulation, then identifying this guy right here as our P and this guy here is our Q, following this setup right here, partial Q with respect to X, so Q with respect to X would be a negative 2X, and then minus partial P with respect to Y, which would just be a 1. And then for our dA, we need to look at that region a little more closely. So we've got the triangle formed by that, and then of course by the x-axis as well. So we'll set this one up vertically. we'll go with dy dx, and that's going to range from 0 to x, the 0 being here, up to the x up here, and then ranging from 0 to 1 across. So 0 to 1. So that is pretty much the exact same thing we did in the previous example. When it comes to now outward flux, the only significant difference here is going to be the formula that we have right here. We'll have partial p with respect to x, which would be the 1, and then we'll have partial q with respect to y. So partial q with respect to y would be the minus 2y. So I'll drop the minus 2y in there, and then the dy dx setup is going to be exactly the same, 0 to x and 0 to 1. And so really using these formulas is going to save us a lot of work compared to what we've done in the past. I would encourage you to take a look at example 4, and you'll see the similarities and how these things work together very, very well. You'll just really want to pay close attention to the setup, the p dx plus q dy versus the p dy minus the q dx.